All right, so now we're going to switch our discussion a little bit by talking about solubility and temperature. So we've kind of touched on this a little bit in prior sections as well, since we had discussed how that delta G equation depends on both factors, but then the entropy is affected by temperature. So this is an observation that we have for most of our ionic salts, and this is a plot, what we call solubility curve, which is just solubility on the y-axis as a function of temperature. And so you can see that for most salts, as temperature goes up, which is going to the right, you can see that solubility also goes up. Now, there's a clear exception here, which is the cerium sulfate salt, right? Actually, its solubility decreases as temperature increases, but that by far is a very, very rare minority. Okay, most salts behave like the ones shown right here, which is that as you increase temperature, its solubility also increases. How do we explain this trend? Well, it's fairly straightforward. We actually explained it much earlier on. Remember that typically for most salts, the delta S of the solution is positive, which means it's favorable, right? So if it's favorable and delta S is affected by temperature, as you increase temperature, this whole term becomes more and more dominant and starts to affect control the value of the delta G of solution. So therefore, at higher temperature, we would expect most salts to dissolve at higher concentration. So what happens with these type of salts? There are exceptions, and typically they have sulfate or sulfide, arsenate. These type of salts are the ones that would dissolve actually less at higher temperature. Well, the reason for these is actually interesting. Their delta S of solution is actually negative, okay? So in other words, they tend to form these more structured hydration shell than what typically we would see in our generic ions, that because of the negative delta S, as the temperature goes up, the solubility of these salts actually decrease, right? Because we have an unfavorable entropy in this case, the salt will dissolve less and less. Now, what about gases? We've talked so far mostly about solids or liquids, right? We haven't really talked about gases. What happens with gases is more like those exception in the salts that we just talked about, which is that they reduce their solubility at high temperature. And we've mentioned this very early on. The reason for this is because a gas has really high entropy. So when you're changing from a gas to aqueous, your delta S of solution is actually decreasing, or you have a delta S that is negative. And because, again, of that T delta S component in your delta G equation, as the temperature goes higher and higher, the delta S becomes more and more dominant, and so your solubility will also decrease, okay? The second factor that affects the solubility of gases is actually pressure, okay? So when we have a gas going from its gas phase into an aqueous phase, the pressure is affected quite a bit because, remember, gases exert pressure, right? So the higher the pressure, this equilibrium between gas and aqueous form is going to be affected. And we can see that in this reaction, if we were to increase pressure of the gas, which is to put more gas on that side, you're going to have the equilibrium shift to the right due to Le Chatelier principle, right? So that means that the higher the pressure, the higher the solubility of gas. And this is something that people have put in practice for many years to try to dissolve gas in water. In fact, there is a equation that we can use to help us figure this out. This is called Henry's law, and it's simply just given as this equation right here, which is just the concentration of a gas that's dissolved in water, which we can also call the solubility of that gas in water, is just equal to a constant, which we call the Henry's law constant, times the pressure of the gas that exists at equilibrium with the solution. Okay, this Henry's law constant is really a measure of the solubility per unit pressure. Okay, so different gases at different Henry's law constant, you can see that most gases has pretty low Henry's law constant, right? So they don't dissolve much at all per atmosphere pressure. But you can see that the sulfur dioxide actually has the highest Henry's law constant, which means that it dissolves quite a bit compared to all the other gases per atm of pressure. So you might wonder why that is. You can find out if you draw the Lewis structure of SO2. It actually looks like this. And the difference between this one and all these other gases here is that this is a polar gas, okay? Whereas these other gases are nonpolar. As you might imagine, if they're nonpolar, they're not going to interact with water that well, right? Whereas the polar gas is going to interact with water better because water is a polar compound. And that's the reason why that gas has a higher Henry's law constant compared to all the other nonpolar gases. One of the most common applications of Henry's law to our everyday life is in the making of carbonated beverages, right? We need to dissolve some amount of carbon dioxide gas in the Coca-Cola or whatever it is that you want to add carbon dioxide to. So here's a simple example of having a pressure of 4 atm, and the question is, what's the solubility of CO2 if you know the Henry's law constant for CO2 being 3.4 times 10 to the minus 2 molar per atm. So all you need to do is to calculate the solubility of CO2 is just to take the pressure, which is 4 atmosphere, times the Henry's law constant, which is 3.4 times 10 to the minus 2 molar per atm. Okay, and this actually gives you 0.136 molar. So the higher the pressure, so that can of soda or bottle of soda actually has a higher pressure inside to maintain that taste of the drink that you like, right? Because you like that fizz or the sparkling feel that the carbon dioxide provides. As soon as you open the bottle, of course, the pressure is going to slowly equilibrate with the atmospheric pressure, which is lower than 4 atmospheres. So it's just 1 atmosphere, depending on where you live. It might be even lower than that. As a result, over time, that soda will turn flat. Flat just means that all the carbon dioxide that's dissolved has basically escaped from the solution because the pressure is lower at that point. Now you can make that CO2 dissolve a little bit more, as we talked about earlier, by giving it lower temperature, by making the temperature lower, because at lower temperature, gases dissolve better based on the entropy factor being more positive at lower temperature.